So last class we have just introduced the decimations and we talked about the classification of decimations, like what are the self-excited, separately excited, shunt, series, all. But we'll see the details of the electrical machines in this course in very detail. So before we move forward, we'll see the voltage generated in the armature circuit. We'll see before that. So already we have discussed these things. Okay, so already we have discussed the constructional features of the DC machines, right? Yesterday. No need to discuss more. So this is a cross-sectional view of the DC machine, right? So where we see the stator and rotor, and in the rotor we have the armature placed in the slots, and in the field winding, that is, it is an electromagnet. So in the field winding we are seeing the winding wound on in the core of the field, right? So this is the main frame. We call it yoke, where actually the fields are installed, right? So next we have also discussed about the commutator, because commutator is required for the rectification purpose, because AC sinusoidal voltage is generated in the armature and which is being converted to DC because of the commutator segment, right? So this is the commutator segment. Now today we'll see how the behavior of a coil inside the magnetic field. Perhaps you have been taught in the class. Is it taught in your class? When a coil is placed and it is rotated inside a magnetic field, what will happen? So okay, before that, so already we talked about this. A rotating machine has two essential parts. Stationary is stator and rotating part is the rotor, right? Then the rotor, of course, in the DC machine, it is referred as armature because the armature winding is in the rotor circuit. Whereas in case of synchronous machine, the rotor actually carries the field, okay? And the stator carries the armature. It is just the reverse. We'll talk about that, why it is. And then the outer diameter of the rotor, it should be smaller than the inner diameter of the stator, right? And therefore the rotating machine can move freely in the air gap. And we know because there are many coils, they are placed in the rotor slots, and when they will move, because they are the coils, when they will move, they will link the flux coming out of the poles or the magnet, right? Magnetic flux, and therefore the voltage will be generated, right? And both the stator and rotor are made from high permeable magnetic materials. I think it is very small. Is it visible to backside? Last bench. If it is not, from tomorrow onwards, I'll try to make large fonts. This is 20 size. Okay, I'll make it large. Don't worry. So, is it visible backside? It might not be because it is small. So tomorrow onwards we'll plan very huge pictures. Okay, huge fonts also. Okay. So the MMF, that is actually it carries the magnetic circuit, which actually produces the flux and which is linking the armature circuit, will produce the EMF in the armature circuit, right? And when the permanent magnet is placed in the stator as a field, so it will produce it is a constant flux, right? So therefore there is no change, and that is the disadvantage of the permanent magnet, placing permanent magnet. Yesterday also we discussed, therefore an electromagnet is preferred, because when the electromagnet is placed, we can change the flux linkage very easily by adjusting the current in the field winding, right? So then a machine is said to be permanent magnet machine when the field is set off by the permanent magnet, and the advantage already we discussed yesterday. And generally the permanent magnet machines are smaller in size, and also the efficiency is more. Why the efficiency is more for permanent magnet? Why? Which loss is not there in the permanent magnet machine? No, they are there. Huh? They are there. Hitless, of course, armature we have hit. It is producing it, right? Only the field winding which incurs the resistive loss, copper loss in the field winding, which is less in case of permanent magnet, because the field winding is not there, right? Today you had machine lab? Huh? Everybody was there. Okay. And tomorrow there is a lab, it is cancelled, okay, because of some physics lab, right? Okay. So it will be scheduled maybe next week, okay? Okay, please silent. So we'll see the generator action, how the EMF actually is produced in the armature coil, okay? So what you are seeing in this figure? Is the figure visible last row? Huh? Not visible. उधर भी नहीं दिख रहा है? Then I have to make very large, because I think this screen is very small. So, figure is visible. Then I have to make it very large, like yesterday today also I have shown first slide. So, because some explanations are needed, so therefore, okay, anyway. So, today you adjust, and maybe tomorrow onwards we'll make very huge pictures. One slide, one picture only. Okay. So, now you can see here it is S, it is mentioned S, right? This is your south pole. Here below, right? It is south pole. Okay? And here it is the north pole. The black color you are seeing, it is the north pole. Okay? Both are the magnets, and we can say it is a permanent magnet. Now, what you are seeing, it is a rotor inside, right? This is the rotor. Is it visible? Huh? And the outside structure is starter where the magnet is fixed, right? Now this rotor is rotating with one coil. Only one coil is placed, that is here, A and B. It is marked as A and B, right? It is not visible perhaps, but it is marked as A and B, which are the conductors of the coil, both the conductors, okay? And now we can see here, the flux will come out from the north pole and it will absorb in the south pole. Again it is making a loop, right? And by that way it is linking the coil, right? This coil is being linked by the flux, right? Flux induced by these magnets, north and south pole. Okay? So now, if this coil will rotate in clockwise direction, in this direction, then what will happen? The flux linkage will change, right? Because, so we know the rate of change of flux linkage induces the voltage, right? Induced voltage. So when the flux linkage will change, it will induce a voltage, right? Now we'll see how it will change the flux linkage. Now this is the rotor, okay? And here the north pole, here the south pole, and the flux is linking. The coil is here on the rotor, right? The armature coil. But we are just taking one coil for the illustration purpose, right? And here again it is rotated in some angle, right? and then again it is rotated. Now what will happen with this rotation? What will happen? This flux is constant, but the change in flux or the flux linkage is varying, right? So then how it will vary the flux linkage? Let us see in this figure. Is this figure visible? No? I think backside it may not be. So you can see, just I cut down the machine and I laid it down. It is straight laid, okay? Because the machine was round, right? Now I cut one side and I laid it. Now your north pole and south pole will be linear, right? It will look like a linear structure, right? And now the flux with the north pole is fixed. We know this is your flux from the north pole, and in the south pole it is negative, right? Okay. So this is your flux. That is the flux from the magnet, right? Now the flux linkage, how it will vary? When the rotor will start from what we have shown there in the figure. From this point, if the rotor starts, okay, so what will happen? At this point particularly, it will link maximum flux, right? Okay, so therefore, here the flux linkage will be maximum here, right? Okay, now it will gradually reduce as the coil will rotate, okay? So as it will reduce, at one point it will become 0. At which point it will become 0? Pi by 2, right? Again it will, at pi it will become maximum negative, right? Then again at which point it will become 0? Okay. So this is the flux linkage. Now if we'll write the equation for the flux linkage, what will be the equation for it? Phi p cos theta. Okay. So this is the flux linkage equation. Now what will be the induced EMF? We know the induced EMF is minus n d phi by dt, right? So here the number of coil is 1, right? Number of turns is 1, so therefore I can write minus d phi by dt, right? So it will become phi p sine of, okay, sine of theta d theta by dt. So what is theta? Theta equal to what? Omega mt, right? Omega m is the speed of the motor or rotor, that omega mt. Just substituting theta equal to omega mt, what will get? Or you can say omega or omega m, whatever. It will become phi p omega sine omega t, right? Okay. So now your induced EMF is phi p omega sine omega t. So this is what it is shown in the lower picture, right? Okay. Now if I will connect a resistor, how I will connect a resistor? Suppose I have no commutator segment. I want to collect the voltage, whatever produced in this coil. So I will put two slip rings as shown in the figure here. This is one slip ring and this is another slip ring. So there are two slip rings connected to each of the side of the, or each of the end of the coil. Okay, one end is connected here at this point and the other end is connected at this point. Okay, now it is connected, the brass is placed on the slip ring. It is not a commutator segment, remember, this is a slip ring I am talking about, right? So slip ring means it is a complete ring and it is made up of copper. Okay, slip ring. Now the brass is pressed to the slip ring here, right? And an external resistor I have connected here. Now the circuit is closed. It is an external load I have connected. Okay. So now some current will pass through it. What will be the current? What will be the equation for current? Can anybody tell? E by R. So that is nothing but it is also sinusoidal, right? It will be phi p omega by R sine of omega t, right? Okay. So this is what will get the equation for voltage, right? Now we'll move to more number of poles. So we talked about here 2 number of poles and 1 coil, right? Now I am taking here 4 poles, 4 number of poles. 4 poles means 2 pairs of poles, right? South, north, south, right? And 4 pair of poles means here is north, this south, north, south. Okay. Now I have 1 coil, single 1 coil. Now what will happen to my voltage? Okay. So now your flux will be, as it will be fixed, right? For each pole. For north pole it is positive and for the south pole it is negative. This is the flux produced by the permanent magnet which is fixed to the stator, right? Now the flux linkage is this one. This is your flux linkage equation, right? And again, if we'll take the derivative of the flux linkage, we'll find the EMF equation, induced EMF equation, right? So this is your flux linkage, phi p cos theta. And again, if I'll find the induced EMF, it will become phi p sin theta or phi p omega sin omega t, right? Now we can see here the structure. Suppose, let us say the rotor is rotating at a speed of omega m. That is we call it mechanical speed. So here we will find a relationship between electrical speed and the mechanical speed. So is it taught in your class previously? Relationship between electrical angle and mechanical angle, mechanical speed and electrical speed. So the speed at which the rotor is rotating is the mechanical speed, okay? Or we can say mechanical frequency, but the frequency of the EMF generated is completely different. It will be electrical frequency. So then we can relate. If you know the electrical frequency and mechanical frequency both, then we can easily relate it. Like in the last picture, what we have seen here in this, each cycle of the voltage is generated when the coil rotates full, like 360 degree, 2 pi, right? When the coil rotates 2 pi, 1 cycle of the voltage is induced, right? Now here in this case, 1 cycle of the voltage is induced when the rotor is rotated at up to which point? When the rotor is rotated up to pi, right? When it is rotated up to pi, it is actually producing the full cycle of EMF, right? Generated EMF. So therefore we can see here that, so this is your, this is a 6-pole machine, right? So here we are showing the 6-pole machine, another illustration. So for the 6-pole machine, again, the frequency will be different. It will be more than the mechanical speed, right? Okay, we can see here. Here the EMF generated, right? Now we'll find the relation, okay? So that means what we can conclude is your electrical angle is equal to P by 2 theta m, that is the mechanical angle, okay? That means as we increase the number of poles in the machine, so your electrical angle is becoming more as the mechanical angle, right? When we are rotating like if I'll take this 4-pole machine, that means when the rotor is rotated by 180 degree, it is giving the full cycle of voltage, right? And when it rotates full, one rotation, that means it is producing 2 cycle of EMF, right? So from this we can indicate that the theta electrical angle is equal to P by 2 theta m, which is the mechanical angle. Mechanical angle means the actual angle by which the rotor rotates. P is the number of poles. Number of poles in the machine. Okay. So P by 2 means it is pole pair, we can say, right? So P is the number of poles here. So therefore I can write omega, that is the electrical speed, is equal to P by 2 omega m, right? Okay. And now if we'll find the frequency, of course from the omega I can find the frequency just by multiplying 2 pi. So your f will be equal to p by 4 pi omega m, right? Okay. Now from this expression I can also find omega m in terms of nm. Omega m is the mechanical speed in radian per second, okay, and nm is the mechanical speed in rpm. Can you find the relationship nm and omega m? So this will be a relationship. It is 2 pi by 60 into nm. Nm is in revolution per minute and omega m is radian per second. If we'll find the relationship, we'll find this 2 pi by 60 into nm, right? So then if I'll express f in terms of the revolution per minute, your expression will become f equal to p by 120 nm, okay? Then your nm will also have relationship with, if the frequency is given, if I want to find the speed of the motor, the speed of the rotor, I can find from this expression, that is nm equal to 120f by p, right? Okay. Okay, so now we can see after the commutator segment is placed in this. So here we can see, so when the two ends of the coil is connected to two commutator segments, here we can see this is your commutator which is insulated at these 2 points, okay? They are not actually connected together. Like slip ring, if I will make, slip ring is completely, it is closed, it gives a closed path, right? But commutator segment means it will give like this, okay? It is your commutator segment. So here we don't have the connection, this here it is filled with the insulations, okay? So therefore, here we are putting a commutator segment just to get the DC output across the load, okay? Now if the commutator segment is placed, now what kind of output we'll get? Of course, this will be your output, right? Okay. So because the resistance is put here, we are plotting here the current. So therefore it will be Em by R. That means peak value of the current will be Em by R, right? But if the voltage, I will plot the voltage, it will also look like a rectifier, half wave rectifier output, right? And it will be Em, right? Okay. Now what is the, if I want to find the DC value of this, DC value means, if I will say find the DC value of this signal, what is the DC value? How I will find the DC value? Huh? RMS value. Who told RMS value? Average value, right? Sorry? Not getting. Can you tell once? Anyway, I am not getting clearly. What is the telling?
Like he is saying, like the power, that is the power in AC and DC is the same. So like the VI in DC, the potentiality into I will be equal to average power.
Okay. Okay. Yes, that is true. So then we need to find the average of this signal. So how will, can you tell me the average of this signal? What will be the average? Huh? Average will be 0. Huh? Then how much it will? Can you find and tell me quickly? Please do it, everybody. What will be the average of this? Use your pen and paper. You don't have paper? EMF for current, whatever, they will same except resistance, right? Yeah. Huh? 2 by pi? Huh? EM, very good. 2 by pi EM. Okay, this will be your average value of this signal, right? Now EM is, if I will express this in terms of these parameters, finally in the speed term I will find 2 pi p by 120 phi p nm, and the average value or average EMF induced in the coil I can write 2 by pi EM, and I can substitute EM from this equation to here in this equation, and I will find P by pi phi p omega m. This is your expression for the DC voltage which we got across the two terminals of the commutator segment. Okay, so this is your DC value. Okay, now so there are different expressions I have shown you here, 2 by pi EM, and if I'll substitute EM in terms of these parameters, it will become P by pi phi p omega m. Again it will become, if I'll substitute in terms of revolution per minute, it will become P by 30 pi p nm. Okay, so now this is your expression for the induced EM or DC voltage across the coil, right? So everybody got this? Or should I show you? Got this? Okay. Okay, so now let us move little more advanced version. One coil we considered only. Now we'll consider the general machine where there are number of coils is NC. Okay. The number of turns per coil is NC, and the number of coils are C. Is mentioned here NC and C. C is the number of coils, total number of coils in the armature winding, and NC is the number of turns in a coil. Like one coil, if I'll see one coil, the coil structure looks like this. So one coil may have several turns. Okay, so it has several turns. So every coil is consisting of NC number of coil, NC number of turns, and there are C number of coils in the armature. Okay, and every coil is consisting of NC number of turns. Okay, now here if we'll consider mostly double layer winding here. Double layer winding means number of slots is equal to number of coils. Please remember this. Okay, number of coils is equal to number of slots. Whatever slots we'll have, slot means where we place the winding, right? So in the armature where we place the winding, that is a slot. We call it slot. And here the number of slots is equal to number of coils in case of two layer winding. Generally the machines have two layer windings, not multi-layer, two layer windings. So therefore number of slots is number of coils. And let us assume that A, this small a is your number of parallel paths. Okay. And this parallel path, because we are not talked more detail about the design aspect, so I am just giving you this information. This number of parallel paths is equal to 2 for a wave winding structure. So A equal to 2 when it is wave wound generator, and A equal to number of poles when it is for wave wound, it is for lap winding. Okay. Because we are not going into the deep into the design aspect, so therefore I skipped the portion because we will not talk about the design aspect because it will take a lot of time. So wave winding and lap winding. Okay. So there are two structures. One is wave winding and other one is lap winding. In wave winding we will have number of parallel paths 2, and in the lap winding it is P, right? Okay. So now I will now find the number of turns, okay, total number of turns per parallel path, so that I can easily calculate the voltage induced in the generator. Okay. So now Na is the turns connected in series, that is the number of coils, okay, number of turns, total number of turns per parallel path. Like if I will have two parallel paths, right, like this, and they are connected to the commutator. Now if I will say here there are Na number of turns and here there is Na number of turns. So then I will say Na is the number of turns, they are connected in series, which represents one parallel path. If I have two parallel paths, it will double the number, right? If it is wave-wound, it will be 2 Na, right? So Na represents the turns connected in series between the negative brush and the positive brush, and it is actually how much it will be. If I will say it will C by A. C is the number of coils divided by number of parallel paths into NC. NC is the number of turns per coil. So per parallel path we have how many number of coils? C by A, and that is multiplied with NC. That will give me number of turns per parallel path. Okay. Okay. So now I will see. So then I can find the average value of the EMF induced in the terminal of the two brushes. I will find then. So EA will be, that is the voltage in each parallel path. If I will find, then it is the voltage across the terminal, right? Across the contacts of the commutator segment. So EA will be now become what? EA will become EC into NA. Okay. So previously we found, so your NA is equal to C by A, NC, and previously we know EC is your average voltage, that is P by phi into omega m phi P, right? So this will give me this result, right? Okay. So now we found the voltage across the terminal, right? Now a little bit will modify in terms of number of conductors in the coil. So how many conductors in a coil? There are two numbers of conductors in each coil. Now we have how many number of coils total? NC, right? NC number of turns. Sorry, one turn has two sides of coil, like I have shown you. One turn has two sides of coil. This is Z, right? Z equal to 2 for each of the turns, right? And there are NC number of coils. So therefore, how many number of conductors will be there? 2NC, right? 2NC into C, because C is the number of coils, right? And then for this, if I will express in terms of number of conductors, I will substitute here NC equal to Z by 2C. Okay. If I will substitute NC equal to Z by 2C here in this equation, above equation, then I will find EA equal to P into Z by 2 pi A phi P omega m. Okay. This equation will find. Okay. So that is EA equal to PZ divided by 2 pi A phi P omega m, right? Now this is your constant term. P is the number of poles, Z is the number of conductors, and 2 pi is a constant and A also a constant. A is the number of parallel paths, right? So therefore your induced EMF will be, I will write it in terms of a constant Ka omega m phi phi. Okay. So what is Ka then? K is a constant, we call it Mason constant sometime, right? So K is sometime we call it Mason constant. Okay. So this equation is valid for both generator as well as motor, because same kind of machine, there is no structural change. So this equation is valid. Then what will say this voltage in case of motor? In case of motor, this EMF is known as the back EMF. But in case of generator, it is known as generated EMF or induced EMF, right? So it is called back EMF in case of motor, right? and K is this, K is a constant, okay, and this constant actually, it is constant for a given machine. It varies. For a particular machine, it is constant. Like in the lab, you are seeing the machine. So for that particular machine, it is constant, right? Okay. Okay, so okay, generally here the assumption is, the important assumption here is that the whole periphery of the rotor is being covered by the poles, magnetic poles. Okay, there is no gap, but actually in practice, or if we'll see a practical motor or generator, the pole surface doesn't cover the whole rotor surface. There is certain gap because of the constructional aspect, right? And if it is more in case of owned rotor, when the field is being owned, right? If it is permanent magnet, we can cover it somehow. But if it is an electromagnet, then it is difficult, right? Okay. So therefore, this is a virtual impossibility, and therefore sometime we take 60% covering, sometime 80%, right? So based on this we can calculate, right, how much flux is being linked to the armature circuit. Okay. Now if the armature of a DC generator supplies a constant current IA to the external load, like we have seen one in the previous circuit, like if we have connected the resistance in the external circuit, then what will be the power generated? Power generated will be PD, right? So PD will be equal to EA into IA. Okay. So EA already we have derived the expression, that is K 5 omega M into IA. That will give us the power. And this power is the power developed, right? It is not the actual power what we are getting across the terminal. It is the power developed at the armature circuit. Okay. It is not the actual power we are getting at the terminal. Why it is not same? Because there are certain losses in the armature, in the right. So after the losses is being deducted, then we'll get the actual power what we'll get at the terminal, right? So therefore I can write this developed power in terms of torque developed. So what is this developed torque in case of generator? Is there any torque developed in case of generator? Huh? Any torque is developed in case of generator? Huh? How it is generated? Huh? You're not getting actually.
He's saying as the axle is rotating, so there should be torque, right?
The torque input we are giving, of course, to rotate the generator we are giving the external torque. That is the input torque, mechanical torque. But there is an induced torque in generator also. What is that induced torque? This is the electromagnetic torque induced. I hope you have studied in your electromagnetic energy conversion. This torque is induced when the current flows in a conductor and that conductor is placed in the magnetic field. There is a torque, right? So when we are connecting the external resistance or external load to the output of the generator, there is a flow of current, right? And as there is a flow of current in the armature, then of course there will be induced torque. Yes. So of course when the induced torque, that induced torque is opposing to the input torque what we are giving, right? And when they both are equal, that means our machine is under steady state. It is very nicely operating. And if there is unbalance between these two torques, that means your induced torque, let us say TD is your developed torque, it should be equal to the mechanical torque we are giving to the generator. If there is unbalance, if suppose let us say TD is greater than Tm, then what will happen to the machine? What what will happen? Can anybody tell? The rotor will decelerate. Okay? When Td is less than Tm, the rotor will accelerate. Okay? The rotor will accelerate. Maybe if it is lesser and lesser, sometime therefore it becomes unstable. The system, the machine becomes unstable because of this phenomenon, right? Okay. So now I can write this Td, the developed torque, is equal to Ka phi Pia, right? So let us say this is Ka phi Pia, because just by substituting here Td equal to Pd by omega m, I can write this equation, right? Just substituting Td equal to Pd by omega m and substituting the Pd expression here in this equation, I will find Td equal to Ka phi Pia, right? So that means your developed torque is directly proportional to phi p, flux per pole, and also it is directly proportional to Ia. Okay, that is the armature current. So whatever current we are drawing, as will increase the load, then the developed torque will be more. Therefore, the speed of we have seen the speed of the generator decreases as the load increases. When you increase the load, you will see it in the lab also. When you increase the load, the developed torque increases. And therefore, your speed also will decrease, right? It will decelerate. Okay. So this is what we studied this today's class. So now can you do this problem? Please do this problem and then we'll stop.